I'm Colin DeGraf. I will be talking more about black holes, but slightly changing gears. And I'm going to talk about the mergers of supermassive black holes, and then what we can learn from that about galaxies. So I'm sure everybody is familiar with these sorts of plots ever since LIGO made its first detection of a gravitational wave coming from a black hole merger. And so here you can see a whole bunch of, the blue ones are the LIGO detections, right? And so there you can see the masses involved in these merging black holes, but it may be a little hard to see, but this is going up to less than 100 solar masses. So these are still very low mass black holes. What I'm interested in is then considering what's going to happen when you start looking at supermassive black holes. So in the semi-near future, we should be getting LISA up and running, which is basically the equivalent of LIGO, but in space and with a much, much longer baseline. So it will be able to detect merging black holes on the order of 100,000 solar masses. And in addition, there are pulsar timing arrays, which basically uses the line of sight to pulsars as a baseline. And so this should be sensitive going up more on the order of 100 million solar masses. So we are expecting to start detecting the mergers of supermassive black holes through gravitational waves quite soon, but it's still very uncertain. How many will there be? How frequently will we see them? And what can we learn about the host galaxies from that? So that's what I'm going to do in this talk. I'll discuss, using the illustrious simulation, what we can learn about what we would expect the supermassive black hole merger rates to be like, how sensitive that is on things like the seed formation mechanisms and on in-spiral times. And then I'll end by looking at how we correlate all of this with the host galaxies. So the very first thing to do is just look at how many mergers do we get in a simulation like Illustris. And so here, both panels are just showing the total number of mergers above a given redshift, where the larger of the two black holes involved in the merger is above a given cut, or where the smaller is above a given cut. So you can see somewhat as you might expect, these merger rates increase as you go to lower redshift. And as you go to higher mass cuts, you obviously have fewer and fewer mergers involved in it. But it's quite smooth. It's pretty well behaved. But you can also see we have a fair number of mergers that involve a very massive black hole. It's pretty rare to have the secondary black hole in the merger be quite massive. So if we can actually just look at the 1D distribution of this. So you can see the larger of the black holes involved in a merger tends to be pretty well distributed across all masses. But the smaller, the one that sort of gets swallowed, they tend to be the lowest masses in the simulation. And this leads to a slight peak in the chirp mass, where chirp mass is a combination of the two, which you can measure using gravitational waves. So we can see we have a pretty well-defined set of mergers here. And the final way we can consider this is just compare M1 and M2, and here's our sort of peak of mergers. Tends to be a relatively low masses at each scale. And we also have sort of a bit of a peak here, and that tends to just be things where you have a massive black hole swallowing one that's been recently seeded. And this is broadly consistent with findings from other simulations as well. But one of the big questions then is, okay, how sensitive will this be if we try and seed the black holes more physically? So this is sort of question one from Ji-Hoon's talk, right? How are black holes seeded? I'm not going to try and get into that. I talked about that last year if you were here at the conference. And if not, there's a paper on arXiv about it. But the idea is we've reprocessed Illustris and changed how the black holes are seeded to try and be more consistent with other physical models for how these black holes would form. And then we look at what that does to this information. So here was our distribution as a function of black hole masses. And here's what it looks like if you only seed black holes through direct collapse. So this is the paper if you want to look at the details of how we do all of that reprocessing, or talk to me afterwards. But what you see is you obviously have far fewer of them, but it also peaks at higher masses in all three panels. And so with direct collapse black holes, you're preferentially seeding at higher redshift. You don't have low redshift seeding, and that biases us towards higher mass mergers. We can see the same thing if we look at the redshift distribution. So the direct collapse model flattens off as you get to low redshift because we have a lot fewer low redshift mergers between direct collapse black holes. And finally, we can sort of see what this does to the M1, M2 plane. So this was the original illustrious simulation. And then this is what happens if you just randomly only seed half of the black holes or 10% of the black holes, which is essentially equivalent, just a shift in normalization. But if you do only direct collapse, you see a very different shape. You're much more likely to have mergers involving similar mass black holes. So we know that trying to model how these black holes are seeded is very important and will change what we expect for merger rates. I have work from a master's student who did a very similar process, but looking at seeding black holes from POP3 remnants instead of through direct collapse. And you see from the original illustrious going down to seeding through population 3 remnants, and you start biasing towards even lower masses. So it's really important to incorporate all of these different seed mechanisms in a self-consistent manner. The next thing you need to consider is time delay. So in many simulations, as soon as two black holes get close enough, they simply instantly merge. That's too fast. So in many cases, it doesn't even model how the black hole gets to the center of the galaxy when the two galaxies merge. And then once it's there, they instantly coalesce without modeling the hardening timescale. So this is some work by Luke Kelly, who had published results showing typical hardening timescales for mergers in illustrious. And you can see, if you consider for all black hole mergers, it gets very high, reaching up in excess of 10 gigayears for a hardening timescale. If you limit yourself to just massive black holes and major mergers, so 10-to-1 mass ratio or closer, then the hardening timescale goes down, but you're still getting up to above 10 to the 8 for the typical hardening timescale. So we really should be considering what this implies. So we've looked at that. So in black here is the original illustrious simulation. This is the number of mergers we're getting as the number density of mergers per year that we might detect. So black is original illustrious, and then if we just impose a fixed delay on all mergers, it shifts. And so you can see at high redshift, obviously putting in a delay changes when they happen. The very first mergers in the simulation then occur much later. But at low redshift, there's very little change. So in fact, putting in a more realistic hardening timescale isn't going to drastically shift how many mergers we would find. It will change the masses of those mergers. So for that fixed 500 megayear or gigayear delay, if we assume that the two black holes which have not yet merged can continue growing at the same efficiency that the post-merged black hole had in the original simulation, then we shift the distribution of chirp mass from the original in black over to red and blue. So we would find that by putting in a more realistic time scale, we're going to start getting more massive mergers, but not too dramatically so. And if you look at what this does, sort of combining the two, typical chirp mass is a function of redshift. So red is original illustrious, which is basically independent of redshift. Chirp mass independent of redshift. But when you put in the proper delay, or if you put in a delay, then at high redshift, it starts getting larger. Yes, what I did is not a proper delay, but it's a first step just looking to see how important it is. So then the last thing we want to look at is, okay, we have all of these merger rates, and we have some sense of how they might be changing if you do a better job modeling seed formation or in-spiral time. But what does that then tell us about host galaxies? So we've discussed the Gini-M20 relation a bit, especially during the discussion yesterday. And Joel gave a nice summary of it, right? It's a combination of how concentrated is the light in a small number of pixels, and how are those pixels distributed. And so what we are essentially saying is, above this line, we might expect those to be mergers as a good way of quantifying when you have a large sample. So this in gray are all the galaxies above 10 to the 9 solar masses at redshift 0.5. And then here are all of the ones which have undergone a black hole merger in the last 500 megayears, which have a mass ratio of 10 to 1 or closer. And so you can see it does preferentially select some up here. And if you then further restrict yourself so you only consider mergers where both black holes were above 10 to the 7 solar masses, then it's an even stronger preference to be in this sort of merger regime. So you can try looking at this in sort of flipping what you're plotting. So we're now going to consider for each object, delta Gini is just how far above or below this merger line it is. So a very positive value represents a stronger morphological merger signature. And so that's plotted here as a function of how long it's been since the most recent black hole merger. And that doesn't really have much in the way of a correlation. And if you do it, again, limit yourself to major mergers, still not a lot. And major mergers where both black holes are large, still not great. There's a bit of one, but not much. But if you put a cut and say, well, let's only consider the ones that have actually been recent, on the order of 500 megayears, then you actually see the red points are preferentially quite high valued compared to ones where the mergers have taken place earlier. So this is suggesting that when you have mergers detected by pulsar timing arrays, for instance, we would start to expect them to be more likely, have a morphological signature of a merger. And we can look at that explicitly. This is just the distribution of how strong the sort of morphological merger signature is. So if we just consider how long has it been since any black hole merger and been within the last 300, 500 megayears, gigayear, 5 gigayears, it doesn't really matter. But that's if you're just considering any black hole merger. If we limit ourselves to relatively major merger, you can see that if it's more recent, it does shift slightly. But this also includes a lot of very low mass black holes, which don't have too much of an effect. So then when we put in the additional constraint, it has to be a major merger between massive black holes. Now we see that there is a bit of an offset here. And in particular, what you want to do is sort of look at what's above versus below the line. So you can see if you have a major merger within 500 megayears, it does mean that you're most likely going to have morphological evidence of a merger. Whereas if you have not had a major merger that recently, it will not, a major black hole merger, then you won't have evidence in the galaxies of a recent merger. So the last thing we can do is actually look at what that looks like in the simulation. So these are all galaxies which have undergone a recent major massive black hole merger. They were only selected based on the black hole merger properties. So this is like if you were to get a pulsar timing array detection and you know nothing else about the host galaxies, these are the sorts of things we might be expecting. And so you can see we have an awful lot of cases where you have evidence of mergers of different types. Sorry, different types of evidence, not different types of mergers. So we have a large sample here, and I'll just show you a couple of those in particular. So here, this is approximately when the black holes merged. And then you can see the same galaxy going to earlier time, so what was happening before the merger took place and after. And so you can see you have a relatively simple image before the merger. Approximately when the black holes merge, you do see a very clear signal, a very clear image of merging galaxies. And then afterwards, you can still continue to see that evidence of a recent merger. So if we just zoom in on that, you can see there are these nice shells of light. So this is just looking at the stellar light. And in particular, this is predicting what JWST would see. So using JWST as a follow-up to a pulsar timing array detection, you can see on the order of 500 megayears, we are still seeing this evidence that the galaxies have undergone a recent merger. We can take a look at another example. This is slightly less massive black holes merging, but again, we have our galaxy, and here you can see this is the merger took place just after this image, and here you've got some of the stars sort of having passed through and falling back, and you have a nicely disturbed galaxy. And one more example, again, we have something where a bit before the black holes merge, you can see there were the two galaxies that are beginning to come together. Right around when the black holes are merging, you still have some of the stars which have passed through the galaxy, and then afterwards, you still have some evidence of these shells. So on the order of a few hundred megayears, we would be able to see it. So conclusions are the cosmological simulations tend to be overly simplistic when it comes to seed formation and in-spiral time for supermassive black holes. And it turns out, if all you care about is the merger rate, the in-spiral time is not too significant, unless you're looking only at high redshift. However, the merger rate and the type of mergers involved will change significantly if you start doing a more physically motivated model for seeding the black holes. And we also find that while low mass or minor black hole mergers tend not to be found in morphologically disturbed galaxies. If you look at either the Gini-M20 relation or just visual classifications, if you're looking at recent major massive black hole mergers, like what you might detect with gravitational waves, you actually do expect that a follow-up observation would be able to see morphological signatures of the recent galaxy merger, as long as the hardening timescale is less than 500 megayears, which is slightly debatable, but among massive major mergers, those tend to have the shortest hardening timescale. So that's a very positive outlook for being able to do these photometric follow-ups to gravitational wave detections. Thank you.
Questions? There in the back? Yeah, you.
So I'm wondering, so you talked about the hardening timescale. I assume that if you take the hardening timescale a gigayear, your morphology effect will go away.
Yes.
Repeat the question.
Yes. So
Yeah.
follow-up question. How often, given the repositioning scheme illustrious, how often do black holes merge before the galaxy?
Okay, so there were two parts to that question. So first asking, well, if the hardening timescale were to be on the order of a gigayear, wouldn't that make the morphological evidence in the host galaxies disappear? And the answer is yes, probably. Not in all cases, but in some of them, yes. And the other question was, I said hardening timescale, but in the text I also was referring to it as in-spiral time. Basically, in something like illustrious, when the secondary black hole when you have the two galaxies merge, the black hole gets repositioned towards the center. It's not instant, but it's also not trying to follow the physics that would actually be involved. So yes, black holes will merge sometimes before the galaxies do, but it's also, I mean, when the galaxies merge is also relatively poorly defined. Part of the problem is, we only have the galaxy information at given snapshots, so we know exactly when the black hole merged, and all we know is the galaxies were not merged in this snapshot, they are here. And furthermore, it's fairly common for the galaxies to not have merged yet, according to the merger tree algorithm, but they will have sort of had a flyby and transferred mass, which adds other complications if you're trying to look at how major the galaxy merger was. But yeah, the short answer would be yes, the black holes will sometimes merge before we find the galaxies to have merged, but there's a lot of uncertainty in there given all of the limits for the simulation.
Hi, just a quick question. I think I was just confused. You said that when you include the hardening timescale or the in-spiral timescale, you develop a correlation of the chirp mass with redshift, even though then at the end you said that the in-spiral times don't depend on
Right.
How do you, yeah.
So it's what you're looking at. So the merger rate is not significantly affected by putting in an in-spiral time. The masses but at any given redshift, the typical masses involved in a merger are affected by that. Because if you give the black holes an extra gigayear time to grow, they'll be bigger when they finally merge.
Oh, so it's because the in-spiral time did not depend on the redshift, but how much they grow in mass during that time does depend on redshift.
Yes, I mean, I don't make it, the growth in that time doesn't depend on redshift explicitly,
No, sure,
but
yes.
And to be clear, the amount of growth during that gigayear, half gigayear, is very weak in terms of how precise the calculation is. The point is trying to get a rough estimate of how important is this, and it's not hugely important, so that's a good thing.
A quick question. If you keep increasing your delay time, what have you called it, at some point you're going to get three-body interactions. Have you looked at what the frequency is of those triplet interactions for a given delay time?
No. We have considered it as, yes, it's an issue that we need to address. I mean, you almost have three-body interactions even without a delay time. It's not that rare to have two mergers, three black holes in a relatively short time scale. So yes, putting in a delay time will definitely start having issues with three-body interaction, but that also starts to become a bit more challenging to try and do just as a post-processing analysis, because we can't actually slingshot one of them out since the simulation originally merged them. But it's something we're aware of and looking into. Yeah.
Okay, so let's thank the speaker again.